So we left off talking about how to find the general antiderivative, and today we're going to focus on what can we do to work on that plus c. So to take this from a general antiderivative to a very specific antiderivative. So as a reminder, a differential equation is an equation that has the differential, whether it's written as something like f prime of x or dy dx, but it has the derivative in it. So you're starting at that derivative layer within our list of functions. So f prime is where you're coming in, and we're going to do some work to find f, which would be the antiderivative. Write a differential equation that uses prime notation containing only x cubed. So we could say f prime of x equals x to the third. Find the antiderivative, right? So the antiderivative is that general antiderivative. Use integral notation to show your work. So I want to take the antiderivative of f prime of x is f of x plus c, which means that the antiderivative of x to the third dx is x to the fourth over 4 plus c. Remember, we increase the power and divide by that new power. So then we have this plus c. And what we've created is a family of functions. Graph two possible children from that family and write the equation for each one. So we know we're going to start with x to the fourth over 4 plus some number, x to the fourth over 4 plus some number. So pick any number you want. I'm going to pick 2, and I'm going to pick -1. And so what you're going to draw is an x to the fourth graph over 4 plus 2 units. It's going to be some very skinny parabola that kind of flattens out a little bit. Same thing here, x to the fourth over 4, but lowered by 1, some sort of skinny parabola that flattens out at the bottom. All right, unbeknownst to you, Mr. Covey was doing the same problem in BC calculus. He wrote his differential equation as f prime of x equals x to the third. Great, we had that. But he also wrote that he knew f of 2 is equal to 5. What this does for us is gives us an initial condition. It tells us that the coordinate point 2, 5 falls on function f. Well, what can we do? We can use that to help us find our plus c. So we know that our differential equation was x to the third, which means that our f of x was x to the fourth over 4 plus c. Well, now I know that f of 2 is going to be 2 to the fourth over 4. Well, 2 to the fourth is going to be our 16 divided by 4 is 4. So I can say that 5 is equal to 4 plus c, which means that c itself is equal to 1. So our specific solution is going to be that f of x is equal to x to the fourth over 4 plus our c value, which is 1. And you can test that by finding f of 2 should come out as 5. Well, 2 to the fourth over 4 is 4, plus 1 is 5. So what we've done is we've taken our family of functions and we have locked in to find the specific function that has that differential equation but also uses the initial condition. So our specific solution is going to be our x to the fourth over 4 that kind of flattens out skinny parabola. That was supposed to go through the point 0, 1. Right, because it fits that initial condition, which means we also go through the point, I might have drawn mine too skinny, 2, 5. So really it should be flattened out like this. All right, example 1 of 4. We have f prime is 3 square root of x plus 3, and f of 1 is equal to 4. So our initial condition, our given information, is that f of 1 is equal to 4. Our differential equation, the part that has a derivative in it, is that f prime of x is equal to 3 square root of x plus 3. So to find f of x, we're going to take the antiderivative of 3. I'm going to write this as x to the 1/2, so I can use the power rule. Well, the antiderivative is going to be equal to, remember the 3 just hangs out. This is going to be increase the power by 1, divide by that new power. I'll clean that up in just a second. Plus 3x plus c. So if that was stressful to you, remember what I'm doing is I'm just breaking up this integral 3x to the 1/2 dx plus the integral of 3 dx, and then taking the antiderivative of each piece, okay? And then we add them together with our plus c. Well, cleaning this up then, I would say 2/3 and the 3 are going to cancel out, so I have 2x to the 3/2 plus 3x plus c is equal to f of x. But I know that f of 1, so if I take 1 and substitute it in for my x value, 3 times 1 plus c is supposed to come out as 4. Well, this allows me then to find my c value. So I'm going to have 4 equals 1 to the 3/2 is just 1. So 2 plus 3 plus c. C is going to be equal to -1, which means that f of x, my specific solution, is 2x to the 3/2 plus 3x minus 1. And you could check that by taking the derivative. You'll get back to where you started, 3x to the 1/2 plus 3. And when you substitute in 1, you'll get an output of 4. Example 2 of 4, we have g prime equals 3 and g of 0 equals 5. So our initial condition is our g of 0 equals 5, which means we go through the point 0, 5. And our differential equation is g prime of x is equal to 3. Mr. Lakin then writes an AWAC joke. This is just a nice little reminder that the average rate of change, the slope of the secant line, will be equal to the instantaneous rate of change, the slope of the tangent line. It's just in there as a joke and a nice little review of some first semester stuff. But ignore it, move on. So g of x, I'm going to take the antiderivative of 3, which will give me 3x plus c. Come on, pen. 3x plus c. But then, if that's going to be my g of x, that's my generic antiderivative. I want this antiderivative to go through my initial condition of 0, 5. So I'm going to plug in 0, 5. When I do that, I end up with the fact that c is equal to 5, because 3 times 0 is 0, which means that my g of x is equal to 3x plus 5. And I can check that in 2 ways. When I take the derivative, I get that g prime is equal to 3, and when I sub in the point 0, I get an output of 5. All right, let's take this up a notch. Find the function f that satisfies all of these conditions. Well, here I'm given information about f double prime. I'm given information about f prime and some information about f, and I'm looking to find my actual function f. Well, if I start at the f double prime layer, so if I'm given information about f double prime, I can go antiderivative once will get me f prime, antiderivative twice will get me f. So I'm going to start by taking the antiderivative of f double prime of x dx is going to get me f prime of x plus c. So the antiderivative of 2 dx, because that's my f double prime, is equal to 2x plus c, which means that f prime of x is equal to 2x plus c, right? Because that f prime is represented there. All right, well, what do I know about f prime? F prime is supposed to go through the point 2, 5. So in goes 2, out comes 5. C is going to be equal to 1, which means that f prime of x is equal to 2x plus 1. And again, I can check that. Taking the derivative, I get 2. Subbing in 2, I get 5. But this question didn't ask me to find f prime, it asked me to find f. Well, I know that if I take the antiderivative of f prime of x dx, that I'll end up with f of x plus c. So the antiderivative of 2x plus 1 is going to be equal to, leave a 2 there, this will become x squared over 2 plus 1x plus c. So what I have just found is that f of x equals x squared plus x plus c. Okay? What else do I know about f? I know that f goes through the point 2, 10. So 10 is equal to 2 squared plus 2 plus c. 10 is equal to 6 plus c. C itself is equal to 4, which means that my final f of x is equal to x squared plus x plus 4. Now you can check this a variety of ways. If I take the derivative, I get f prime is 2x plus 1, and the second derivative is 2. If I plug in 2, 2 squared is 4, plus 2 is 6, plus 4 is 10, so that meets that condition. And I know that I found my specific family member because I'm locked in to going through these specific points. Last one just gets a little tricky with our notation. So we have little g is equal to 2x, big G of 3 is 4. So I know that this is a coordinate point 3, 4. Find big prime of g, knowing that g prime is equal to little g. Okay. Well, I know that if I was given g prime, I could go backwards a layer to get g, right? If we think about our list of functions, well, it tells me that g prime is equal to just little g. Well, little g was 2x. So if I take the antiderivative of 2x, I get x squared plus c. And so what I've done, come on, pen, is I've taken the antiderivative of g of x dx, gets me capital G of x plus c, because the other way that I could have thought about little g was big G prime. Now that I know g of x is x squared plus c, I can use my initial condition of 3, 4 to figure out that c is going to be equal to negative 5, which means that my actual g of x final answer is x squared minus 5, which you can check by taking the derivative of g gets you g prime, which is 2x. And when you sub in 3, 3 squared is 9, minus 5 is 4. Something to note, okay, remember when you're given something like this, g prime is equal to g of x, it's just a substitution, right? That means that the antiderivative of g prime of x is equal to the antiderivative of g of x. All right, so just be really careful with your notation in terms of g, g prime, where is little g. Basically, within the list of functions, right, where are you coming in to start talking about derivatives versus antiderivatives? Are you working the layer up or are you working a layer down? As a summary, you're going to take the antiderivative, then use your initial condition or your given condition to find the specific antiderivative, the specific family member. We're no longer talking about a whole family of functions, talking about a specific member that's locked in to a given point, just like that first one should have been my red parabola because it goes through the point 0, 1 and also through the point 2, 5, having the shape of x to the 4th over 4.